I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about Young's double slit experiment. Now let us see the brief outline of module 4. In the previous lecture we have discussed the very basics related to light and optics, that is Huygens principle and the superposition of waves. And with this background, today we are going to see Young's double slit experiment. So let us see how we are going to do our discussion today. First, we'll be seeing the experimental setup for the Young's double slit experiment. Then we'll see how the fringes are formed. And then we'll do the qualitative treatment and understand the conditions for constructive interference and also the conditions for destructive interference. Now coming to Young's double slit experiment, it is a classical example of interference effect in light waves. So we are going to study about interference using this Young's double slit experiment. Now what is this interference? When two waves of the same frequency and having constant phase difference moving in the same direction superimpose on each other, interference takes place. So these terms are very important. We will consider them with the same frequency, having a constant phase difference, and they have to superpose on each other moving in the same direction. Then they will interfere. We get the interference pattern. Now what we have in this experiment? In this experiment, the original light source need not be coherent. It becomes so after passing through the narrow slits. So here if you see, this is our original source. And then we have two slits S1 and S2, which are placed equidistant from this source. S1 and S2 are placed equidistant from the source. So now the light coming from this source will pass through these two slits, and the light that emerges from these two slits will now interfere and give us the interference pattern. So what we see here is two light rays pass through the two slits separated by a distance d, means the distance between the two slits is considered to be small d. And then the light coming out from these two slits strike the screen at a distance L from the slits. So this is the screen, and we consider the distance between the screen and the source to be L, or in some experiments or in some notation we may write it as capital D also. Small d here is the distance between the two slits, and capital D or L here represents the distance between the source. These are the two slits which act as sources now from here to the screen. So this is the basic thing we are going to see in this experiment. Now let us understand what is happening here when light passes through these two slits. So we are considering this is one slit and this is another slit. Slit A and slit B. Now you imagine if light consists of particles, means we have had a long discussion about these nature of light, whether it is particle or wave, and then we have finally concluded that light exhibits dual nature, particle nature as well as wave nature. So first we will think about the particle nature. You imagine that light behaves as particles. Then if this is the source through which the light is coming out, and we have a screen here, so there should be one spot here or one band here corresponding to the light that is coming from the slit. And also we have another slit B here through which light is coming. There will be another band on the screen corresponding to these two. So if light consists of particles, the final screen should show only two thin stripes, one corresponding to each slit. This is from the slit A and this is from the slit B. It should have only two spots or two stripes on the screen. But if light is a wave, each slit will serve as a new source of wavelets. So you can see here, if we are taking this A as a source, so this is giving rise to new wavelets. These are the wavelets from the source A. And the same way from B also, we have the waves. We are calling them as secondary waves. So each slit is now acting as a new source and sending out wavelets. And then the final screen will show the effects of interference. This is according to Huygens principle. We have studied in Huygens principle that each point on the wavefront acts as a secondary source and sends out secondary wavelets. Now these secondary waves, when they are superimposing on each other, we get the interference pattern. That is how we see the effect of interference on the screen. We do not just see two spots on the screen, but we will see different bands, a series of bands on the screen that is due to interference. So now let us understand how these bands are formed. And now we will understand this diagram. With the help of this diagram, we will understand the effect of interference and also how do we number these fringes. Okay, the same setup we have considered. We have a source S here. Light coming from the source is passing through two slits A and B. These two are separated by a small distance D. Now, this source acts as a secondary wavelets. It is sending out secondary waves. So, these are the secondary waves. Now, this also B acts as a secondary source and sending out secondary wavelets. Now, these waves that are coming from the two slits will superimpose on each other, and depending upon the superimposition, you will have bright and dark bands on the screen. So, if this is the source, well, the two slits are the source. Of course, they are secondary source, and we have a screen here. So, we understood, we have discussed right now that if it is particles, we would have had only 2 points on the screen, one corresponding to the slit A and one corresponding to the slit B. But what you see here on the screen is a pattern like this, which we call it as interference pattern. Means the waves that are coming out from these two sources superimpose on each other and give rise to this interference pattern. So how is this interference pattern and how do we number them? So the light that is coming out straight, when they superimpose, you will have a central bright fringe. This is called the central bright fringe. The central fringe is a bright fringe. Why bright, why dark, we are going to discuss in the experiment. First, I am just going to give you a picture what we are going to discuss. So we will call it as M is equal to 0. The central fringe is numbered as 0. Okay, and then after the bright fringe, you will have a dark fringe. This is a dark fringe with M is equal to 1. This is the first dark fringe. So on either side of the central bright fringe, you have dark fringes. So this is again the second dark fringe here. So in some cases, we will write this as 0 means the first dark fringe. So this is +1 and then you will have -1 on the other side. So after the dark fringe, you will again have a bright fringe, then a dark fringe, bright fringe. So how we are numbering them? Let us now just focus on these numbering. So the first one, the central bright fringe is M is equal to 0. And the next bright fringe is here. This is M is equal to +1. +1 because it is in the upward direction from 0. Whenever we take a graph with 0 as a reference point, then all those values which are in the upward direction along the positive y-axis, we take it as positive, and in the negative y-axis, we take them as negative. So this is M is equal to +1 and the next bright band is M is equal to +2. Now if you see below, we are taking m is equal to -1. This is the bright band on the other side. M is equal to -1 and m is equal to -2. Now we will see the dark bands also. If we have considered this is the dark band which is represented by m is equal to 0. So this is the dark band in the upward direction. So m is equal to +1 and m is equal to +2. M is equal to -1. So what you see here is you have a central bright fringe with bright and dark fringes alternating each other, and that is how we are numbering them. Now we will see the qualitative wave based explanation for Young's experiment. The interference pattern of dark and bright bands produced by the light passing through two closely spaced narrow slits can be explained by the addition or superposition of wavelets originating from the two slits. So what we have considered here is a source. Light coming from a source is passing through two slits which are placed equidistant, and the light that is coming out from these two narrow slits will interfere with each other, and then you will have the interference pattern. Now the length of the path that each wave travels and reaches a particular spot on the screen determines the phase of the wave at that location. So here two things we need to understand. Length of the path means it is the distance traveled by the wave from the source to that point it reaches on the screen. And what is phase? Phase tells about the state of vibration of the particle. So this phase depends upon the length of the path the wave travels. Now locations where the two waves arrive in phase are bright. We have discussed, the central band is a bright band, and on either side we have the dark bands and bright bands alternating each other. So when do we get a bright band? So when the waves arrive in phase. So again we have seen that this phase depends upon the length of the path the wave has traveled. So if they are arriving in phase, you get a bright band. And when the two waves arrive with a different phase, they are not in phase, but there is a difference in phase, then they are darker. And the locations where the waves arrive completely out of phase, then they are completely dark. So to explain this point, I would like to give you an example. So let us take the first wave. If this is the first wave, then you have the second wave also exactly in phase. Means if you have a crest here, you also have a crest here. So the crest falls on the crest and the trough falls on the trough. So they are arriving in phase. So when they are arriving in phase, the point is bright. And here when they arrive completely out of phase, I will take another wave. So in this case, if we consider a wave like this. So what is the difference here? If this is a crest here, this is a trough. So the crest falls on the trough. There is a complete phase difference in these two waves. So they are arriving out of phase and they are completely dark. Now, let us understand the entire pattern here. Interference pattern can be explained using the idea of interference of wavelets. So we are considering the wavelets that are originating from two sources which are placed very close to each other. So constructive interference occurs when crest from the wavelets overlap. When a crest of one wave falls on the crest of the other wave, then there is constructive interference. We call it as constructive interference and you get double-sized crests. Now, destructive interference means no light is present. Means the wavelets are out of phase and they cancel each other. Out of phase here means the crest falls on the trough. So crest falls on the crest, you are getting double-sized crest. But when a crest falls on a trough, they cancel out each other. They are out of phase and then you will have no light there. So you see the example here. So these are the two sources, S1 and S2. Very small sources. The width of the sources should be very small. They are sending out secondary wavelets. So these are the secondary wavelets. This is the secondary wavelet from this source. Now what you are observing here is these wavelets are superimposing on each other. So when they are superimposing on each other, these points where the crest of one wave falls on the crest of the other wave, you will have a bright light. Bright means it is constructive interference. Now the crest falls on the crest and you will get a double-sized crest. So this corresponds to constructive interference. Now here if you see, there are also regions where a crest falls on a trough. So these points where a crest falls on a trough, they cancel out each other, and this point is dark, or there is no wave, which you call it as destructive interference. So what we are observing here, the central spot is bright here. This is a bright light, which we have numbered as 0. Then after the central bright fringe, we had the dark fringe or the dark band where we say no wave. This is due to destructive interference. Then after the dark fringe, you have a bright fringe, which we call as due to constructive interference. So on the other side also, you have the same way. These are the points where a crest falls on a trough and they cancel out each other. There is no wave and the position is dark. This is due to destructive interference. And again, these points corresponds to bright light because the crest falls on the crest. So overlap of crest and trough produces zero disturbance, that is destructive interference. When a crest falls on a crest, we are having a double-sized crest, and that is constructive interference. Now let us see the diagram. If we are just representing it diagrammatically, so we have the source, the original source. We are going to derive the expression now for the path difference as well as the phase difference, because everything now depends upon the path difference. If they are traveling the same path, they are in phase, and if they are in phase, they are giving constructive interference, which gives rise to a bright band. But when they arrive out of phase, then it leads to destructive interference, which gives us a dark band. So let us try to derive the expression for that. Now see this diagram. We have a source, and these are the two slits S1 and S2, which are separated by a small distance d. So d is the distance between the two sources. Now we have waves coming from S1 and also S2. Of course, we have seen the wave representation. Now we are focusing on the length of the path that is traveled by the wave. Now the wave coming from S1 is reaching the point P. Let us talk about two waves that are arriving at the point P. Now the distance traveled by the wave coming from the point S1 is R1. So this is the distance traveled by the wave, length of the path. Now from S2, whatever waves that are coming, they are reaching the point P, and the distance traveled is R2. The length of the path here is R2, R1 and R2. Now if you see clearly, there is a difference in the path traveled by the two rays. The ray coming from S2 is traveling a larger distance, or the path length is more when compared to the one coming from S1. Now to calculate the difference in path, that is what we are calling as a path difference, which we denote by delta. Let us write the expression from the geometry of the figure. So what we are going to do now is drop a perpendicular from here, from this point, on to S2P. So this is the perpendicular we are dropping. So this angle is 90 degree and this makes an angle theta with the vertical here. Now, if I consider this right angle triangle, this is the right angle 90. I will consider this right angle triangle and write sine theta. So what is sine theta equal to? Sine theta is opposite side upon hypotenuse. So in this figure, the opposite side is this, which we are representing by delta. This is represented by delta and this is represented by d. So sine theta is equal to opposite side upon hypotenuse. So the opposite side is delta and the hypotenuse is d. So sine theta is equal to delta upon d. And now from the geometry of the figure, if you see, if you have dropped a perpendicular from S1 onto this, from here the distance is the same. The distance traveled by the two waves is the same. Only difference is delta. So we will call this as the path difference. Delta can be written as R2 minus R1. We can get delta from R2 minus R1. The length of this path minus the length of this will give us the path difference, that is R2 minus R1. Now we can write R2 minus R1 is equal to d sine theta. So from here, what we can write for delta, this implies delta is equal to d sine theta. Sine theta is delta upon d. So delta will be equal to d into sine theta. So let us consider this as 1, this as 2. Now you compare 1 and 2. So if you compare 1 and 2, both are the formulae for delta. On the left hand side, we have delta. So delta is equal to R2 minus R1. So R2 minus R1 is equal to d sine theta. So this is an important relation which we are going to take forward. Delta is equal to R2 minus R1. That is d sine theta from these two equations. Now, for a bright fringe that is produced by constructive interference, the path difference must be either 0 or it should be an integral multiple of wavelength. So this is the condition. So when do we get a bright fringe? When the path difference is 0, means they should travel exactly the same distance. That means there is no path difference between the two, or the path difference should be an integral multiple of wavelength. Only in these cases you will get a bright fringe. So if delta is equal to d sine theta, in order to get a bright fringe, it should be equal to n lambda, where n can take the value 0, plus or minus 1, plus or minus 2 and so on. So if n is equal to 0, we have delta is equal to 0. Delta is equal to 0 means there is no path difference. There is no path difference. So the path difference must be either 0 or it should be an integral multiple of wavelength. So we can take n is equal to 1, then you will have delta is equal to lambda, 2 lambda, 3 lambda and so on. So these are integral multiples of lambda, that is the wavelength. So whenever the path difference is 0 or an integral multiple of lambda, you will get a bright fringe. So n is called here the order number. If n is equal to 0, we are getting the 0th order maximum, and when is equal to plus or minus 1, we call it as first order. N is equal to 2 is the second order and so on. Plus or minus 1 we have already discussed. Plus 1 in the upward direction and minus 1 in the downward direction from the central fringe. Now, when destructive interference occurs, a dark fringe is observed. So, when do we have destructive interference? So, when the path difference is an odd multiple of half the wavelength. It is an odd multiple of half the wavelength, then we get a dark fringe. So, what is the condition we are going to write? Delta is equal to d sine theta. And when it will be dark, when it is an half multiple of wavelength. So n plus half lambda, or the same thing when we are having n plus half into lambda, I can as well write it as, take it as LCM and write it as 2n plus 1 by 2 into lambda, or 2n plus 1 into lambda by 2. All three mean the same. So what we are writing here, n plus half lambda or 2n plus 1 lambda by 2. Now if you see, if you keep n is equal to 0, for n is equal to 0, what do we get? Lambda by 2. So what is lambda by 2? It is a odd multiple of half the wavelength. Now keep n is equal to 1. This is for n is equal to 0. Keep for n is equal to 1. So when n is equal to 1, you have 2 into 1 is 2 plus 1, 3 lambda by 2. N is equal to 2 gives us 2 2s are 4 plus 1 5, 5 lambda by 2. So what we are getting here, lambda by 2, 3 lambda by 2, 5 lambda by 2 and so on. So whenever you are having a path difference as odd multiple of half the wavelength, 1, 3, 5, they are all odd multiples of half the wavelength. Lambda by 2, lambda is a full wavelength. Wavelength is always represented by lambda. So lambda by 2 represents half wavelength. So what is the condition? So if the path difference is an odd multiple of half the wavelength, then we get a dark fringe. So we have seen two conditions. The condition for the bright fringe or the constructive interference, delta is equal to d sine theta, should be equal to n lambda, where n can take all the integers. If it is 0, it will be the central bright fringe, and 1, 2 and so on gives us the other bright fringes. But for dark fringe, we have delta is equal to 2n plus 1 into lambda by 2. So where we are having the odd multiples of half the wavelength. Now determination of the distance of bright and dark fringe from the central spot on the screen. Means if this is the central spot and this is the bright fringe, so what is the distance between the central bright fringe and the next bright fringe? What is the distance between the two? So we are going to determine the distance of the bright and the dark fringe. So if you have a dark fringe here, so we can also find the distance between the central bright fringe and the dark fringe from the central spot on the screen. So how we are going to find it? Now light, same setup we are going to use. Light from a narrow slit S is illuminating. This is a monochromatic source. What is monochromatic? Monochromatic always represents light of single wavelength. Mono means single. Chromatic means single color. A single color will have a particular wavelength. So light of single wavelength is allowed to fall on two narrow slits. So always we are mentioning that the slit should be very narrow. So A and B are the two slits. So this is a source, monochromatic source. Light from here is passing through two narrow slits A and B. These two are placed very close to each other, small d. And the width of each slit is 0.03 millimeter. So when we are talking about narrow slits, how narrow the slits are? So the width of the slit is 0.03 millimeter. So this width of the slit or this width of the slit is only 0.03 millimeter, and they are about 0.3 millimeter apart. Means this distance small d is equal to 0.3 millimeter. This is also too small. So we are keeping them very close to each other. The width of the slit is 0.03 and the distance between the two slits is 0.3 millimeter. Now since A and B are equidistant from S, so if you consider the distance from S to A or the distance from S to B, they are same, they are equal. So we are calling them as equidistant. So light waves from S reach A and B in phase because they are traveling the same distance. They are reaching the point A and B in phase. That is what we are calling A and B as coherent sources because the distance traveled by them is the same. They are in phase. So now these two sources A and B are considered to be coherent sources. So A and B act as coherent. Coherent always represents same phase. Now, according to Huygens principle, wavelets from A and B spread out. Overlapping takes place onto the right side of AB. Right side of AB means if you have the sources, the light that is coming from the source is passing through the two slits. Let me make it equidistant. So this is the source. This is A and this is B. So the light is reaching here and from here you will have a screen. So the wavelets that are coming from A and the wavelets that are coming from B, there is overlapping. Okay, overlapping on the right side. So this is the right side of AB. Now when a screen XY is placed at a distance of 1 meter from the slits. So this is the source. We will call this also as source, secondary source. This is the screen. There we are naming it as XY. And it is placed at a distance of 1 meter from the source. So now, if you are considering this distance, small d, we have taken as 0.3 millimeter. This distance, capital D, is 1 meter. So the distance between the source and the screen should be very large compared to the width of the slit. Then what happens when a screen is placed at a distance of 1 meter from the slits? Equally spaced alternate bright and dark fringes appear on the screen and they are called interference fringes. So what we have seen here, at the center you will have a bright fringe and then dark, bright, and so on. Dark, bright, and so on. You will have on the screen, you will have alternate bright and dark. If the central one is bright, this will be dark, bright, and so on. This is how we number them. This is dark. So they are alternating each other. So alternate bright and dark fringes appear on the screen and they are called as interference fringes or bands. Now at O on the screen, if I consider the central point, this is O. This is the point O. So the waves travel equal distance, so they arrive in phase. So the distance traveled from here and here is equal, so they arrive in phase. So whenever they arrive in phase, that gives rise to constructive interference and they will interfere constructively and a bright fringe is observed at the point O, which we are calling it as the central bright fringe. Now, let us understand this diagram. Let D be the distance between the two sources. So, we have considered this is the distance between the two sources A and B. Now, this is the screen XY, which is placed parallel to AB. This is AB. This is AB. And this is XY. So, XY is placed parallel to AB and it is placed at a distance of D, capital D from the source. The screen is placed at a distance of capital D and let C be the midpoint. Let C be the midpoint of AB. Sorry, this we will not consider as C. So, let us consider C as the midpoint of AB and O is the midpoint on the screen. We will consider this as O, which is equidistant from A and B. So, this point O must be equidistant from A as well as B. So, P is a point at a distance X from O. Now, if you consider a point P, where the waves from these two slits A and B reach, this point P is at a distance x from the central, because we are going to find what will be the distance at which the next bright fringe is formed. We have the central bright fringe because the waves are traveling equal distances. So we are getting a central bright fringe. Now we are considering a point P at which the waves are arriving in phase. So we will imagine there is another bright fringe here. So what is the distance from the central bright fringe to this fringe? That is x. Now the same diagram we have seen. Now waves from A and B meet at P in phase or out of phase depending upon the path difference between the two waves. Now these waves that are coming from A to P and the waves coming from B to P, they are interfering here. And when they interfere here, depending upon the path they travel, they may be in phase or they may be out of phase. If they are in phase, means they are arriving in phase at this point P, we will have constructive interference, that is a bright band. And when they arrive out of phase, we will consider it as a dark band. So now we are going to calculate that path difference. So for that, what we do, A, B are the two slits separated by a small distance D. Capital D is the distance between the source and the screen. Screen we have considered as XY. We have taken C as a center point on AB and O is the center point on the screen. So if this is the central point, we are going to calculate X, the distance from O to P. Now what we are going to do is draw AM perpendicular to BP. So BP is this length of the path the wave travels from B. We are going to drop a perpendicular AM. So this is the right angle. Now if you have to calculate the path difference, means the difference in the path traveled by the two waves from A and B. So how do we get that path difference? Delta will be BP minus AP. BP is the distance traveled by the wave from P to the point P, and AP is the distance or the length of the path from the source A to the point P. So delta is equal to AP minus BP minus AP, and AP is equal to MP. AP here is what? This is the path AP and this is MP. Once we have dropped perpendicular in such a way that AP is equal to MP. So AP is equal to MP. Now if I have to find delta is equal to BP minus AP, in place of AP I will substitute MP. So BP minus AP will be equal to BP minus MP. So what is BP minus MP? This is BP and this is MP. So BP minus MP gives us BM. So we get BM. So what we are trying to find here is the path difference. Delta here represents the path difference. The path difference is denoted by delta. So the difference in path traveled by the two waves, we are calling it as path difference. And that how we are getting from BP minus MP, that is BM. So the path difference simply is given by BM. Now we will consider this right angle triangle. ABM is the right angle triangle. This is the right angle. And from the geometry of the figure, we can write sine theta is equal to, this is angle theta. Sine theta is equal to opposite side upon hypotenuse. So what is the opposite side here? BM. And what is the hypotenuse? AB. Sine theta is equal to BM upon AB. So now we can write for BM. So BM will be now equal to AB sine theta. And just now what we have seen, BM is nothing but the path difference delta. So delta is equal to AB sine theta. And AB is nothing but the distance between the two slits, that is small d. So we are going to write the path difference delta is equal to d sine theta. So BM, that is the path difference, is equal to d sine theta. This is from the geometry of the figure from the right angle triangle ABM. Now, if theta is small, this angle obviously is very small. Angle is very small because the two slits A and B are placed very close to each other, 0.3 millimeters. They are separated by a distance of 0.3 millimeter. So the angle will be very small. So if theta is small, sine theta is equal to theta. So we are going to replace this sine theta with theta. So what happens to the path difference now? The path difference BM is equal to delta will be written as d theta, because theta is very small. For sine theta we are writing theta. So delta will now be equal to d theta. Now consider the right angle triangle COP. What is a right angle triangle COP? C is the central point here on AB. O is the central point on the screen. Now we are going to consider this triangle COP. And this angle is theta from the geometry of the figure. This angle is theta. Now how do we write tan theta? Tan theta is what? Opposite side upon adjacent side. We are going to write the formula for tan theta now. Tan theta is equal to what? This is theta. So what is the opposite side? OP. What is the adjacent side? OC. So we are going to write tan theta is equal to OP upon OC. So we will write this as OP upon OC. Now what is OP equal to? We have considered it to be X. The distance of the point P from the central spot, we have considered it as X. And the distance between the source and the screen, we have taken as capital D. So this is capital D. COE is nothing but capital D. So we are going to substitute for OP X and for OC D. So tan theta is equal to X upon D. And since theta is very small, again we consider tan theta is equal to theta. So theta will be equal to what? X upon. Now here we have delta is equal to d theta and we have theta is equal to X upon D. So if we substitute the value of theta in this equation, we get delta is equal to d into X upon D. So simply for d theta, in place of theta, we have substituted X upon D because we have derived it from this figure. Theta is equal to X upon D. So delta is equal to small d into X upon capital D. Now by the principle of interference, condition for constructive interference is the path difference should be an integral multiple of lambda. We have already discussed this. Whenever the path difference is an integral multiple of lambda, we get constructive interference. And now what is the path difference? We have got small d into X upon capital D. So when we substitute for path difference, small d into X upon capital D, or I can write it as should be equal to n lambda. So this is what? Path difference. Path difference is given by small d into X upon capital D is equal to n lambda. So if I have to write for X, so X will be equal to n lambda capital D upon small d. So this will be the expression for X, the distance at which the next bright fringe is formed from the central fringe. And n here denotes the order of the fringe. N denotes the order of the fringe. So here when we are writing X into D by D is equal to n lambda, we are writing X is equal to capital D by D into n lambda. Or if n is equal to 1, we have capital D by D into lambda. So we are writing for n is equal to 1. Now this equation gives the distance of the nth bright fringe from the central point O. So what is x here? It is the distance of the nth bright fringe. Here if I am talking n is equal to 1, so will be the first bright fringe from the point O. So we have derived the expression for the distance of the nth bright fringe from the central point O. Now what is it for destructive? So we have already seen the condition for destructive interference, that the path difference should be an odd multiple of half the wavelength. So 2n plus 1 into lambda by 2. So what is the path difference we have got? We have already derived that path difference lambda is equal to 2n plus 1 into lambda by 2. So we are going to substitute this condition and get x. So x will now be equal to capital D by D into 2n plus 1 by 2 into lambda. So this is what we are going to get, because if you substitute n is equal to 0, so what you get here is d by d into lambda by 2. So for n is equal to 0, you have x is equal to lambda d by d. And for n is equal to 1, you get x is equal to, if this is 1, 2 plus 1, 3 lambda d by d, 2d, sorry, we have 2d. So x is equal to, if we are taking this as 0, we have lambda by 2. So always it is odd multiples of half the wavelength. So we have x, that is the distance of the dark fringe from the central fringe. So this gives the distance of the nth dark fringe from the point O. So what you have now on the screen is a series of alternate bright and dark bands on the screen from the central fringe. So we have derived the conditions for the central fringe and the bright fringe and dark fringe on either side. So in the next class, we are going to derive an expression for the width of the fringe. That is the distance between two bright fringes or two dark fringes. Thank you and see you in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.